All right. Wow, full room. I'm just going to jump right in. About 15 years ago, my stepmother, and we'll call her Frances for the sake of this conversation, became ill. She had aches through her whole body. She had weakness. She had difficulty standing. And by the time they got her to the hospital, she had paralysis in her arms and legs. And it was a terrifying experience for her and obviously for us as well. Turns out she had something called Guillain-Barré syndrome. Has anybody heard of this before? I'm just curious. Oh, lots of people. Good. Well, not good. Hopefully you haven't had firsthand experience with it. It's an autoimmune disorder, and it's a really interesting one. It's triggered by some kind of external factor, which is fairly common with autoimmune disorders. But what's interesting about this one is that the antibodies will directly attack what's called the myelin sheath that wraps around the axon, that long section in nerve cells. And it essentially eats away at it, such that the signals become very diffuse. And so you can imagine these symptoms of pain and weakness and paralysis are all quite logical when you understand what's going on. The good news is that it's treatable, either through plasmapheresis, where they filter your blood outside your body, or antibody therapy, and that was successful. The latter was successful for Frances. What was interesting also was her reaction to this condition. She became much more disciplined about her health. She started eating right, exercising more. She started doing Qigong and Tai Chi to improve her health, and she was committed to having this kind of event never happen to her again. And what this event really underscores for me is how amazing the human body is, and how something as simple as the act of breathing or interacting with the world is actually a pretty miraculous thing. And it's actually an act of bravery to a certain extent. There are so many forces in the world, so many allergens and bacterial infections and various things that can cause problems for us. And so you might be wondering, why the hell are we talking about this at a microservices talk? But just as breathing is a miraculous act of bravery, so is taking traffic in your microservice architecture. You might have traffic spikes, you might have a DDoS attack, you might introduce changes into your own environment that can take the entire service down and prevent your customers from accessing it. And so this is why we're here today. We're going to talk about microservice architectures which have huge benefits, but also talk about the challenges and the solutions that Netflix has discovered over the last 7 years, wrestling with a lot of these kinds of failures and conditions. So I'm going to do a little bit of an introduction. I'll introduce myself. And I'm going to spend a little bit of time level setting on microservice basics, so we're all using the same vocabulary as we go through this. And then we'll spend the majority of our time talking about the challenges and solutions that Netflix has encountered. And then we'll spend a little bit of time talking about the relationship between organization and architecture and how that's relevant to this discussion. So by way of introduction, hello, I'm Josh Evans. I started at Netflix, had a career before this, but this is the most relevant part. In 1999, I joined Netflix about a month before the subscription DVD service launched. I was in the e-commerce space as an engineer and then a manager, and got to see that transition from an e-commerce perspective in terms of how we integrated streaming into the existing DVD business. 2009, I moved over right into the heart of streaming, managing a team that's today called Playback Services. This is the team that does DRM and manifest delivery, recording telemetry coming back from devices. I also managed this team during a time when we were going international, getting onto every possible device in the world, and just this side project of moving from data center to cloud. So it's actually quite an interesting and exciting time. For the last 3 years, I've been managing a team called Operations Engineering, where we focus on operational excellence. Engineering, velocity, monitoring and alerting, so think about things like delivery, chaos engineering, a whole wide variety of functions to help Netflix engineers be successful operating their own services in the cloud. So you'll see that there's an end date there. I actually left Netflix about a month ago, and today I'm actually thinking a lot about Arianna Huffington. Catching up on my sleep for the first time in quite some time. Taking some time off, spending time with my family, trying to figure out what this work-life balance thing looks like. Actually, this will be mostly life balance, which will be great. Big shift from what I was doing before. Netflix, as you know, is the leader in subscription internet TV service. It produces or licenses Hollywood, independent, and local content, has a growing slate of pretty amazing originals, and at this point is at about 86 million members globally and growing quite rapidly. Netflix is in about 190 countries today and has localized in tens of languages. That's user interface, subs, and dubs. Thousands of device platforms. And all of this is running on microservices on AWS. So let's dig in and let's talk about microservices from the abstract sense. And I'd like to start by talking about what microservices are not. I'm going to go back to 2000, my early days at Netflix, when we were a web-based business where people put DVDs in their queue and had them shipped out and returned and all of that. So we had a pretty simple infrastructure. This was in a data center, hardware-based load balancer, actually very expensive hardware that we used as our Linux hosts, running a fairly standard configuration of an Apache reverse proxy and Tomcat, and this one application that we called Java Web. It's kind of everything that was in Java that our customers needed to access. Now, this was connected directly to an Oracle database using JDBC, which was then interconnect with other Oracle databases using database links. The first problem with this architecture was that the code base for Java Web was monolithic, in the sense that everybody was contributing to one code base that got deployed on a weekly or bi-weekly basis. And the problem with that was when a change was introduced that caused a problem, it was difficult to diagnose. We probably spent well over a week troubleshooting a slow-moving memory leak. It took about a day to happen. We tried pulling out pieces of code and running it again to see what would happen. And because so many changes were rolling into that one application, this took an extended period of time. The database was also monolithic in even a more severe sense. It was one piece of hardware running one big Oracle database that we called the store database. And when this went down, everything went down. And every year, as we started to get into the holiday peak, we were scrambling to find bigger and bigger hardware so that we could vertically scale this application. Probably one of the most painful pieces from the engineering perspective, other than the outages that might have happened, was the lack of agility that we had because everything was so deeply interconnected. We had direct calls into the database. We had many applications directly referencing table schemas. And I can remember trying to add a column to a table was a big cross-functional project for us. So this is a great example of how not to build services today, although this was the common pattern back in the late 90s and early 2000s. So what is a microservice? Does anybody want to volunteer their understanding or definition of what a microservice is? I'm sort of curious what I'll get here. Somebody, some brave soul, there we go. What's a microservice?
Context-bound and data ownership.
Say it again.
Context-bound and data ownership.
Context-bound and data ownership. I like that. I'm going to give you the Martin Fowler definition. This is a good place to start. That's definitely a key piece. I'm going to read this to you so you don't have to. Microservice architecture style is an approach to developing a single application as a suite of small services, each running in its own process and commuting with a lightweight mechanisms, often an HTTP resource API. So I think we all know this. It's a somewhat abstract definition. It's very technically correct, but it doesn't really give you enough of the flavor, I think, of what it means to build microservices. When I think about it, I think of it as this extreme reaction to that experience that I had back in 2000 with monolithic applications. Separation of concerns being probably one of the most critical things that it encourages. Modularity, the ability to encapsulate your data structures behind something so that you don't have to deal with all of this coordination. Scalability, they tend to lend themselves to horizontal scaling if you approach it correctly. And workload partitioning, because it's a distributed system, you can take your work and break it out into smaller components, which make it more manageable. And then, of course, none of this really works well, from my perspective, unless you're running it in a virtualized and elastic environment. It is much, much harder to manage microservices if you're not doing it in this kind of environment. You need to be able to automate your operations as much as possible, and on-demand provisioning is a huge, huge benefit that I wouldn't want to give up if I were building this. Going back to that theme of the human body and biology, you can think of microservices also as organs in an organ system, and these systems that then come together to form the overall organism. So let's take a look at the Netflix architecture a little bit and see how that maps. There's a proxy layer that's behind the ELB called Zool that does dynamic routing. There's a tier that was our legacy tier called NCCP that supported our earlier devices plus fundamental playback capabilities. And there's our Netflix API, which is our API gateway that today is really core to our modern architecture, calling out into all of the other services to fulfill requests for customers. This aggregate set that we've just walked through, we consider our edge service. There's a few auxiliary services as well, like DRM, that support this, that are also part of the edge. And then this soup on the right-hand side is a combination of middle tier and platform services that enable the service to function overall. To give you a sense of what these organs look like, these entities, here are a few examples. We have an A/B testing infrastructure, and there's an A/B service that returns back values if you want to know what tests a customer should be in. We have a subscriber service that is called from almost everything to find out information about our customers, a recommendation system that provides the information necessary to build the lists of movies that get presented to each customer as a unique experience. And then, of course, there's platform services that perform the more fundamental capabilities. Routing to get so microservices can find each other, dynamic configuration, cryptographic operations, and then, of course, there's the persistence layers as well. These are the kinds of objects that live in this ecosystem. Now, I also want to underscore that microservices are an abstraction. We tend to think of them very simplistically as, here's my nice horizontally scaled microservice, and people are going to call me, which is great if it's that simple, but it's almost never that simple. At some point, you need data. Your service is going to need to pull on data for a variety of reasons. It might be subscriber information, it might be recommendations, but that data is typically stored in your persistence layer. And then for convenience, and this is really a Netflix approach that I think many others have embraced, but definitely specific to Netflix as well, is to start providing client libraries, and this were mostly Java-based, so client libraries for doing those basic data access types of operations. Now, at some point, as you scale, you're probably going to need to front this with a cache because the service plus the database may not perform well enough. And so you're going to have a cache client as well. And then now you need to start thinking about orchestration. So I'm going to hit the cache first. Then if that fails, I need to go to the service, which is going to call the database. It'll return a response back. And then, of course, you want to make sure you backfill the cache so that it's hot the next time you call it, which might just be a few milliseconds later. Now, this client library is going to be embedded within the applications that want to consume your microservice. And so it's important to realize from their perspective, this entire set of technologies, this whole complex configuration is your microservice. It's not this very simple stateless thing, which is nice from sort of a pure perspective, but it actually has these sort of complex structures to them. So that's the level set on microservices. And now let's go ahead and let's dig in on the challenges that we've encountered over the last 7 years and some of the solutions and philosophies behind that. So I love junk food. And I love this image because I think in many cases, the problems and solutions have to do with the habits that we have and how we approach microservices. And so the goal is to get us to eat more vegetables in many cases. We're going to break this down into 4 sort of primary areas that we're going to investigate. There are 4 dimensions in terms of how we address these challenges. Dependency, scale, variance within your architecture, and how you introduce change. We're going to start with dependencies, and I'm going to break this down into 4 use cases within dependencies. Intra-service requests. This is the call from microservice A to microservice B in order to fulfill some larger request. And just as we were talking about earlier with the nerve cells and the conduction, everything's great when it's all working, but when it's challenging, it can feel like you're crossing a vast chasm. In the case of a service, calling another service, you've just taken on a huge risk by just going off process and off your box. You could run into network latency and congestion. You could have hardware failures that prevent routing of your traffic. Or the service you're calling might be in bad shape. It might have had a bad deployment and have some kind of logical bugs, or it might not be properly scaled. And so it can simply fail or be very slow, and you might end up timing out when you call it. The disaster scenario, and we've seen this more than I'd like to admit, is the scenario where you've got one service that fails. With improper defenses against that one service failing, it can cascade and take down your entire service for your members. And God forbid you deployed that bad change out to multiple regions if you have a multi-region strategy, because now you've really just got no place to go to recover. You just have to fix the problem in place. So to deal with this, Netflix created Hystrix, which has a few really nice properties. It's got a structured way for handling timeouts and retries. It has this concept of a fallback. So if I can't call service B, can I return some static response or something that will allow the customer to continue using the product instead of simply getting an error? And then the other big benefit of Hystrix is isolated thread pools and this concept of circuits. If I keep hammering away at service B and it just keeps failing, maybe I should stop calling it and fail fast, return that fallback, and wait for it to recover. So this has been a great innovation for Netflix. It's been used quite broadly. But the fundamental question comes in. Now I've got all my Hystrix settings in place, and I think I've got it all right. But how do you really know if it's going to work? And especially, how do you know it's going to work at scale? The best way to do this, going back to our biology theme, is inoculation, where you might take a dead version of a virus and inject it to develop the antibodies to defend against the live version. And likewise, fault injection in production accomplishes the same thing. And Netflix created FIT, the fault injection test framework, in order to do this. You can do synthetic transactions, which are overridden basically at the account or the device level. Or you can actually do a percentage of live traffic. So once you've determined that everything works functionally, now you want to put it under load and see what happens with real customers. And of course, you want to be able to test it no matter how you call that service. Whether you call it directly, whether you call it indirectly, you want to make sure that your requests are decorated with the right context so that you can fail it universally, just as if the service was really down in production without actually taking it down. So this is all great. This is sort of a point-to-point perspective. But imagine now that you've got 100 microservices, and each one of those might have a dependency on other services or multiple other services. There's a big challenge about how do you constrain the scope of the testing that you need to do so that you're not testing millions of permutations of services calling each other. This is even more important when you think about it from an availability perspective. Imagine you've only got 10 services in your entire microservice infrastructure, and each one of them is up for 4 nines of availability. That gives you 53 minutes a year that service can be down. Now that's great as an availability number, but when you combine them, all the aggregate failures that would have happened throughout that year, you actually will end up with 3 nines of availability for your overall service. And that's somewhere in the ballpark of between 8 and 9 hours a year, a big difference. And so to address this, Netflix defined this concept of critical microservices, the ones that are necessary to have basic functionality work. Can the customer load the app, browse and find something to watch? It might just be a list of the most popular movies, hit play and have it actually work. And so we've taken this approach and identified those services as a group, and then created FIT recipes that essentially blacklist all of the other services that are not critical. And this way we can actually test this out, and we have tested this for short periods of time in production to make sure that the service actually functions when all those dependencies go away. So this is a much simpler approach to trying to do all of the point-to-point interactions, and has actually been very successful for Netflix in finding critical errors. So let's now talk about client libraries, shifting gears completely. When we first started moving to the cloud, we had some very heated discussions about client libraries. There were a bunch of folks who had done great work from Yahoo, who had come to Netflix, who were espousing the model of bare bones REST. Just call the service, don't create any client libraries, don't deal with all of that, just go bare bones. And yet at the same time, there are really compelling arguments for building client libraries. If I have common logic and common access patterns for calling my service, and I've got 20 or 30 different dependencies, do I really want every single one of those teams writing the same code or slightly different code over and over again? Or do we want to simply consolidate that down into common business logic and common access patterns? And this was so compelling that this is actually what we did. Now, the big challenge here is that this is a slippery slope back towards having a new kind of monolith, where now our API gateway in this case, which might be hitting 100 services, is now running a lot of code in process that they didn't write. This takes us all the way back to 2000, running lots of code in the same common code base. It's a lot like a parasitic infection, if you really think about it. This little nasty thing here is not the size of Godzilla. It's not going to take down Tokyo, but it will infest your intestines. It'll attach to your blood vessels and drink your blood like a vampire. This is called a hookworm, and a full-blown infestation can actually lead to pretty severe anemia and make you weak. And likewise, client libraries can do all kinds of things that you have no knowledge of that might also weaken your service. They might consume more heap than you expect. They might have logical defects that cause failures within your application. And they might have transitive dependencies that pull in other libraries that conflict in terms of versions and break your builds. And all of this has happened, especially with the API team, because they're consuming so many libraries from so many teams. And there's no cut and dry answer here. There's been a lot of discussion about this. It's been somewhat controversial even over the last year or so. The general consensus has been, though, to try to simplify those libraries. There's not a desire to move all the way to that bare bones REST model. But there is a desire to limit the amount of logic and heap consumption happening there. And you want to make sure that people have the ability to make smart, thoughtful decisions on a case-by-case basis. So we'll see how this all unfolds. This is sort of an ongoing conversation. And mostly I'm bringing up here so that all of you can be sort of thoughtful about these trade-offs and understand that. Now, persistence is something that I think Netflix got right early on. There isn't a war story here about how we got it wrong. And let me tell you how we got it right. We got it right by starting off thinking about the right constructs and about CAP theorem. I assume how many people are not familiar with CAP theorem? I'm just sort of curious. OK, so we've got a few. Let's go ahead and level set here. This is the simplest definition that allowed me to get my brain around what this really was. In the presence of a network partition, you must choose between consistency and availability. In this case here, you might have a service running in network A, and it wants to write to databases a copy of the same data into databases that are running in 3 different networks. Or in AWS, this might be 3 different availability zones. The fundamental question is, what do you do when you can't get to one or more of them? Do you just fail and give back an error, or do you write to the ones you can get to and then fix it up afterwards? Netflix chose the latter and embraced this concept of eventual consistency, where we don't expect every single write to be read back immediately from any one of the sources that we've written the data to. And Cassandra does this really well, and it has lots of flexibility. So the client might write to only one node, which then orchestrates and writes to multiple nodes. And there's a concept of local quorum, where you can say, I need this many nodes to respond back and say that they've actually committed the change before I'm going to assume that it's written out. And that could be one node if you really want to take on some risk in terms of the durability, but you're willing to get very high availability. Or you can dial it up the other way and say, I want it to be all the nodes that I want to write to. So let's move on. I'm just going to briefly talk about infrastructure, because this is a whole topic unto itself. But at some point, your infrastructure, whether it's AWS or Google or things that you've built yourself, is going to fail. The point here is not that Amazon can't keep their services up. They're actually very, very good at it, but that everything fails. And the mistake, if I were going to put blame on anybody in terms of what happened in Christmas Eve of 2012, when the ELB control plane went down, was that we put all our eggs in one basket. We put them all in US East 1. And so when there was a failure there, and by the way, we've induced enough of our own to know that this is also true, there was no place to go. And so Netflix developed a multi-region strategy with 3 AWS regions, such that if any one of them failed completely, we can still push all the traffic over to the other surviving regions. So I did a talk on this earlier in the year. So I would encourage you to take a look at it if you want to get really deep into the multi-region strategy and all the reasons that it evolved the way that it did. But at this point, I'm going to put a pin in this. I'm going to move forward. So let's talk about scale now. And with scale, I'm going to give you three cases: the stateless service scenario, the stateful service scenario, these sort of fundamental components, and then the hybrid, similar to the diagram that we were looking at earlier, where it's an orchestrated set of things that come together. OK, another question. What's a stateless service? Anybody have an idea? Want to throw out their idea, their definition of it? Ah, brave soul, good.
Nothing really persistent in the sense that there's no information that can change from request to request.
OK, that's close. That's interesting. I start with, it's not a cache or a database. You're not storing massive amounts of data. You will frequently have frequently accessed metadata cached in memory. So there's the non-volatile nature of that, or configuration information. Typically, you won't have instance affinity, where you expect a customer to stick to a particular instance repeatedly. And the most important thing is that the loss of a node is essentially a non-event. It's not something that we should spend a lot of time worrying about. And it recovers very quickly. So you should be able to boot up and spin up a new one to replace a bad node relatively easily. And the best strategy here is one going back to biology, is one of replication. Just as with mitosis, we can create cells on demand. Our cells are constantly dying and constantly being replenished. Autoscaling accomplishes this. I'm sure most people are familiar with autoscaling, but I can't underscore enough how fundamental this is and how much this is table stakes for running microservices in a cloud. You've got your min and your max. You've got a metric you're using to determine whether you need to scale up your group. And then when you need to have a new instance spun up, you simply pull a new image out of S3 and you spin it back up. The advantages are several. You get compute efficiency because you're typically using on-demand capacity. Your nodes get replaced easily. And most importantly, actually, is when you get traffic spikes, if you get a DDoS attack, if you introduce a performance bug, autoscaling allows you to absorb that change while you're figuring out what actually happened. So this has saved us many, many times. Strongly recommend it. And then, of course, you want to make sure it always works by applying chaos. Chaos Monkey was our very first sort of chaos tool. And it simply confirms that when a node dies, everything still continues to work. This has been such a non-issue for Netflix since we've implemented Chaos Monkey. I kind of want to knock wood as I say that. This just doesn't take our service down anymore. Losing an individual node is very much the non-event that we want it to be. So let's jump in. Let's talk about stateful services, and they are the opposite, obviously, of a stateless one. It is databases and caches. It is sometimes a custom app, and we did this, a custom app that has internalized caches, but of like large amounts of data. And we had a service tier that did this, and as soon as we went multi-region and tried to come up with generic strategies for replicating data, this was the biggest problem we had. So I strongly recommend you try and avoid storing your business logic and your state all within one application, if you can avoid it. Now, in this case, what's meaningful is, again, the opposite of stateless, which is that the loss of a node is a notable event. It may take hours to replace that node and spin up a new one. So it is something that you need to be much more careful about. So I'm going to talk about, and I'm going to sort of tipping my hand here, two different approaches for how we dealt with caching to sort of underscore this. And again, as I said, we had a number of people who were from Yahoo who had experience using HA proxy and squid caches, and a pattern where they had dedicated nodes for customers. So a given customer would always hit the same node for the cache, and there was only one copy of that data. The challenge is, of course, when that node goes down, you've got a single point of failure, and those customers would be unable to access that service. But even worse, because this was in the early days, we didn't have proper historics settings in place. We didn't have the bulk heading and the separation and isolation of thread pools. And so I can still remember being on a call where one node went down, and all of Netflix went down along with it. It took us 3.5 hours to bring it back up, to wait for that cache to refill itself before we could fulfill requests. So that's the anti-pattern, the single point of failure pattern. And going back to biology, redundancy is fundamental. We have 2 kidneys so that if one fails, we still have another one. We have 2 lungs. Same thing. Now, it does give us increased capacity, but we can live with only one of them. And just as your human body does that, Netflix has approached an architecture using a technology called EV cache. And EV cache is essentially a wrapper around memcached. It is sharded, similar to the SQUID caches, but multiple copies are written out to multiple nodes. So every time a write happens, not only does it write it out to multiple nodes, but it writes them into different availability zones. So it sprays them across and separates them across the network partitions. And likewise, when we do reads, reads are local because you want that local efficiency, but the application can fall back to reading across availability zones if it needs to get to those other nodes. This is a success pattern that has been repeated throughout. EV cache is used by virtually every service that needs a cache today at Netflix, and it's been highly useful to us in lots of good ways. Now let's talk about the combination of the two. This is the scenario we talked about earlier where you've got a hybrid service. It's very easy in this case to take EV cache for granted. Let me tell you why. It can handle 30 million requests per second across the clusters we have globally, which is 2 trillion requests per day. It stores hundreds of billions of objects in tens of thousands of memcached instances. And here's the biggest win here. It consistently scales in a linear way such that requests can be returned within a matter of milliseconds, no matter what the load is. Obviously, you need to have enough nodes, but it scales really well. And we had a scenario several years ago where our subscriber service was leaning on EV cache a little bit too much. And this is another anti-pattern worth talking about. It was called by almost every service. I mean, everybody wants to know about the subscriber and what's their customer ID and how do I go access some other piece of information. It had online and offline calls going to the same cluster, the same EV cache cluster. So batch processes doing recommendations, looking up subscriber information, plus the real-time call path. And in many cases, it was called multiple times, even with the same application, within the life cycle of a single request. It was treated as if you could freely call the cache as often as you wanted to, so that at peak, we were seeing load of 800,000 to 1 million requests per second against the service tier. The fallback was a logical one when you were thinking about it from a one-off perspective. I just got a cache miss. Let me go call into the service. The problem was the fallback also, when the entire EV cache layer went down, was still a fallback to the service and the database. And that's the anti-pattern. The service and the database couldn't possibly handle the load that EV cache was shouldering. And so the right approach was to fail fast. So with this excessive load, we saw EV cache go down. It took down the entire subscriber service. And the solutions were several. The first thing is stop hammering away at the same set of systems for batch and real-time. Do request level caching so you're not repeatedly calling the same service over and over again as if it was free. Make that first hit expensive and the rest of them free throughout the life cycle of the request. And something we haven't done yet, but will very likely do, is embed a secure token within the devices themselves that they pass with their requests. So if the subscriber service is unavailable, you can fall back to that data stored in that encrypted token. It should have enough information to identify the customer and do the fundamental operations for keeping the service up for that customer so they can get some kind of reasonable experience. And then, of course, you want to put this under load using chaos exercises, using tools like Fit. Now let's move on and let's talk about variance. This is variety in your architecture. And the more variance you have, the greater your challenges are going to be because it increases the complexity of the environment you're managing. I'm going to talk about 2 use cases. One is operational drift that happens over time. The other is the introduction that we've had recently over the last few years of new languages and containers within our architecture. Operational drift is something that's unintentional. We don't do this on purpose, but it does happen quite naturally. Drift over time looks something like setting your alert thresholds and keeping those maintained because those will change over time. Your timeouts and your retry settings might change. Maybe you've added a new batch operation that should take longer. Your throughput will likely degrade over time unless you're constantly squeeze testing, because as you add new functionality, that's likely to slow things down. And then you can also get this drift sort of across services. Let's say you found a great practice for keeping services up and running, but only half of your teams have actually embraced that practice. So the first time we go and reach out to teams and say, hey, let's go figure this out. Let's go get your alerts all tuned. Let's do some squeeze testing. Let's get you all tuned up and make sure service is going to be highly reliable and well performant. And usually we get a pretty enthusiastic response on that first pass. But humans are not very good at doing this very repetitive sort of manual stuff. Most people would rather be doing something else, or they need to do their day job, like go and build product for their product managers, the next A/B test we need to roll out. And so the next time we go, we tend not to get that same level of enthusiasm when we say, hey, sorry, but you're going to need to go do this again. You can really take a lesson again from biology with this concept of the autonomic nervous system. There's lots of functions that your body just takes care of, and you don't have to think about it. You don't have to think about how you digest food. You don't have to think about breathing, or you would die when you fell asleep. And likewise, you want to make sure you set up an environment where you can make as many of these best practices subconscious, or not required for people to really spend a lot of time thinking about. And the way that we've done that at Netflix is by building out a cycle of continuous learning and automation. And typically that learning comes from some kind of incident. We just had an outage. We get people on a call. We hopefully alleviate customer pain. We do an incident review to make sure that we understand what happened, and then immediately do some kind of remediation, hopefully, to make sure, at least tactically, that that works well. But then we do some analysis. Is this a new pattern? Is there a best practice that we can derive from this? Is this a recurring issue where if we could come up with some kind of solution, it would be very high impact? And then, of course, you want to automate that wherever possible. And then, of course, you want to drive adoption to make sure that that gets integrated. This is how knowledge becomes code, and it gets integrated directly into your microservice architecture. Over the years, we've accumulated a set of these best practices. We call it production ready. This is a checklist, and it's a program within Netflix. Virtually every single one of these has some kind of automation behind it and a continuous improvement model where we're trying to make them better. Whether that's having a great alerting strategy, making sure you're using auto-scaling, using Chaos Monkey to test out your stateless service, doing red-black pushes to make sure that you can roll back quickly, and one of the really important ones, staging your deployments so that you don't push out bad code to all regions simultaneously. Of course, all of these are automated. And now I'm going to jump over. I'm going to talk about polyglot and containers. This is something that's come about really just in the last few years. And this is an intentional form of variance. These are people consciously going, I want to introduce new technologies into the microservice architecture. When I first started managing operations engineering about 3 years ago, we came up with this construct of the paved road. The paved road was a set of sort of best-of-breed technologies that worked best for Netflix, with automation and integration sort of baked in, so that our developers could be as agile as possible, that if they got on the paved road, they were going to have a really, really efficient experience. We focused on Java, and what I'm now going to call bare bones EC2, which is a bit of an oxymoron, but basically using EC2 as opposed to containers. While we were building that out, and very proud of ourselves for getting this working well, our internal customers, our engineering customers, were going off-road and building out their own paths. Started innocuously enough with Python, doing operational work, made perfect sense. We had some back office applications written in Ruby. And then things got sort of interesting when our web team said, you know, we're going to abandon the JVM and we're actually going to rewrite the web application in Node.js. That's when things got very interesting. And then as we added in Docker, things become very challenging. Now, the reasons we did this were logical. It made a lot of sense to embrace these technologies. However, things got real when we started talking about putting these technologies into the critical path for our customers. And it actually makes a lot of sense to do so. Let me tell you why. So the API gateway actually had a capability, or has a capability, to integrate Groovy scripts that can act as endpoints for the UI teams. And they can version every single one of those scripts, so that as they make changes, they can deploy a change out into production that has onto devices out in the field, and have that sync up with that endpoint that's running within the API gateway. But this is another example of the monolith. Lots of code running in process with a lot of variety and people with different understandings of how that service works. And we've had situations where endpoints got deleted, or where the script or some script went rogue, generated too many versions of something, and ate up all of the memory available on the API service. So again, a monolithic pattern to be avoided. And so the logical solution is to take those endpoints and push them out of the API service. And in this case, the plan is to move those into Node.js, little Node.js applications running in Docker containers. And then those would, of course, call back into the API service, and now we've got our separation of concerns again. Now we can isolate any breakage or challenges that are introduced by those Node applications. Now, this doesn't come without a cost. In fact, there's a rather large cost that comes with these kinds of changes, and so it's very important to be thoughtful about it. The UI teams that were using the Groovy scripts were used to a very efficient model for how they did their development. They didn't have to spend a lot of time managing the infrastructure. They got to write scripts, check them in, and they were done. And so trying to replicate that with a Node.js and Docker container methodology takes a substantial amount of additional work. The insight and triage capabilities are different. If you're running in a container and you're asking about how much CPU is being consumed or how much memory, you have to treat that differently. You have to have different tooling, and you have to instrument those applications in different ways. We have a base AMI that was pretty generic that was used across all of our applications. Now that's being fragmented out and more specialized. Node management is huge. There is no architecture out there or no technology out there today that we can use out of the box that allows us to manage these applications the way that we want to in the cloud. And so there's an entirely new tier called Titus being built that allows us to do all the workload management and the equivalent of auto scaling and node replacement and all of that. So Netflix is making a fairly huge investment in that area. And then all the work we did over the years running in the JVM with our platform code, making people efficient by providing a bunch of services. Now we have decisions to make. Do we duplicate them? Do we not provide them and let those teams running in Node have to write their own direct REST calls and manage all of that themselves? So that's being discussed, and there's a certain amount of compromise happening there. Some of the platform functionality is going to be written natively in Node, for example. And then, of course, anytime you introduce a new technology into production, we saw this when we moved to the cloud. We saw this every time we've done a major re-architecture. You're going to break things, and things will break in interesting and new ways that you haven't yet encountered. And so there's a learning curve before you're actually going to become good at this. And so rather than one paved road, we now have a proliferation of paved roads. And this is a real challenge for the teams that are centralized, that are finite, that are trying to provide support to the rest of the engineering organization. So we had a big debate about this a few months ago, and the stance where we landed was the most important thing was to make sure that we really raised awareness of costs so that when we're making these architectural decisions, people are well informed and they can make good choices. We're going to constrain the amount of support and focus primarily still on JVM, but obviously this new use case of Node and Docker is pretty critical, and so there's a lot of energy going into supporting that. And then, of course, logically, we'd have to prioritize by impact with a finite number of people who can work on these types of things. And where possible, seek reusable solutions. Delivery is relatively generic, so you can probably support a wide variety of languages and platforms with delivery. So that's one example there. One other example is client libraries that are relatively simple can potentially be auto-generated. So you can create a Ruby version and a Python version and a Java version. So we're seeking those kinds of solutions. Again, this is one of those places where if there's no one cut and dry right way to do this, hopefully this is good food for thought if you're dealing with these kinds of situations. So let's talk about that last element now, change. What we do know is that when we are in the office, when we are making changes in production, we break things. This is outages by day of week. Lo and behold, on the weekend, things tend to break less. Here's the really interesting one by time of day, 9 o'clock in the morning, boom. Time to push changes, time to break Netflix. So we know that happens. And so the fundamental question here is, how do you achieve velocity but with confidence? How do I move as fast as possible and without worrying about breaking things all the time? The way that we address that is by creating a new delivery platform. This replaced Asgard, which was our workhorse for many years. This new platform was a global cloud management platform, but also an automated delivery system. And here's what's really critical here. Spinnaker was designed to integrate best practices such that as things are deploying out into production, we can integrate these lessons learned, these automated components, directly into the path for delivery. In the pipeline we see here, it's using two things that we value highly. Automated canary analysis, where you put a trickle of traffic or some traffic into a new version of the code with live production traffic. And then you determine whether or not the new code is as good or better than the old code. and stage deployments, where you want to make sure you deploy, I'm getting the 5-minute sign, where you want to make sure you deploy one region at a time so that if something breaks, you can go to other regions. You can see the list here of other functions that are integrated, and long-term, the production-ready checklist we talked about earlier is fodder for a whole wide variety of things that long-term should be integrated into the delivery pipeline. I'm cheating a little bit here because of time constraints. Luckily, I can. And I did a talk last year at reInvent that might be of interest to you if you really want to dig into how these functions deeply integrate with each other. How does the production-ready, performance and reliability, chaos engineering integrate with Spinnaker and continuous delivery, monitoring systems, et cetera? So I would encourage you to check it out. Now I'm going to close this out with a short story about organization and architecture. In the early days, there was a team called Electronic Delivery. That's actually the first version of streaming was called Electronic Delivery. We didn't have a term streaming back then. In fact, originally we were going to do download and had a hard drive in some kind of device. And the very first version of the Netflix-ready device platform looked something like this. It had fundamental capabilities like networking capabilities built into the platform, functionality around security, activation, playback, and then there was a user interface. The user interface was actually relatively simple at the time. It was using something called a queue reader, where you'd go to the website and add something into your queue and then go to the device and see if it showed up. What was also nice is this was developed under one organization, which was called Electronic Delivery, and so the client team and the server team were all one organization, so they had this great, tight working relationship. It was very collaborative, and the design that they had developed, or that we had developed, was XML-based payloads, custom response codes within those XML responses, and versioned firmware releases that would go out over long cycles. Now, in parallel, the Netflix API was created for the DVD business to try and stimulate applications, external applications that would drive traffic back to Netflix. We said, let 1,000 flowers bloom. We hoped that this would be wildly successful. It really wasn't. It didn't really generate a huge amount of value to Netflix. However, the Netflix API was well poised to help us out with our UI innovation. It contained content metadata, so all the data about what movies are available, and could generate lists. And it had a generalized REST API, JSON-based schema, HTTP-based response codes. It's starting to feel like a more modern architecture here. And it did use an OAuth security model, because that's what was required at the time for external apps. That evolved over time to something else. But what matters here is that from a device perspective, we now had fragmentation across these two tiers. We now had two edge services functioning in very, very different ways. One was REST-based, JSON, OAuth. The other was RPC, XML, and a custom security mechanism for dealing with tokens. And there was a firewall, essentially, between these two teams. In fact, because the API originally wasn't as well scaled as NCCP, there was a lot of frustration between teams. Every time API went down, my team got called. And so there was some friction there. We really wanted them to be able to get that up and running. But this distinction, this unique services, protocols, schemas, security models, meant that, God forbid, you were a client developer and you had to span both of these worlds and try to get work done. You were switching between completely different contexts. And we actually had examples where we wanted to be able to do things like return limited duration licenses back with the list of movies that were coming back for the user interface. So when you click through and hit play, it was instantaneous, as opposed to having to make another round-trip call to do DRM. So because of this, I had a conversation with one of the engineers, a very senior engineer at Netflix, and I asked him, what's the right long-term architecture? Can we do an exercise here and go figure this out? And this was a gentleman named Peter Stout, and of course, very thoughtfully, the first question he had to me seconds later was, do you care about the organizational implications? What happens if we have to integrate these things? What happens if we have to break the way we do things? Well, this is very relevant to something called Conway's Law. Does anybody, I'm hearing some laughter, so whoever laughed first, tell me what Conway's Law is.
The relationship between your services will look like the relationship with your company.
All right, good. Here's the more detailed explanation. Organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. Sort of very abstract. I like this one a little better. Any piece of software reflects the organizational structure that produced it. Here's my favorite one. You have 4 teams working on a compiler, you'll end up with a 4-pass compiler. So Netflix had a 4-pass compiler. That's where we were. And the problem with this is the tail wagging the dog. This is not solutions first, this is organization first that was driving the architecture that we had. And when we think about this, this is essentially going back to this illustration we had before. We had our gateway, we had NCCP, which is handling legacy devices, plus playback support, we had API. This was just a mess. And so the architecture we ended up developing was something we call Blade Runner, because we were talking about the edge services. And the capabilities of NCCP became decomposed and integrated directly into the Zool proxy layer, the API gateway, and then appropriate pieces were pushed out into new, smaller microservices that handle more fundamental capabilities like security and features around playback, like subtitles and dubs and serving metadata. So the lessons learned here. This gave us greater capability and it gave us greater agility long term. By unifying these things and thinking about the client and what their experience was, we were able to produce something much more powerful. And we ended up refactoring the organization in response. I ended up actually moving on. My whole team got folded under the Netflix API team, and that's when I moved over to operations engineering. And that was the right thing to do for the business. Lessons learned, solutions first, teams second, and be willing to make those organizational changes. So I'm going to briefly recap. I have 0 minutes, so I'm going to go over just a couple of minutes, just so we can wrap up cleanly here. So microservice architectures are complex and organic, and it's best to think about them that way. And their health depends on a discipline and about injecting chaos into that environment on a regular basis. For dependencies, you want to use circuit breakers and fallbacks and apply chaos. You want to have simple clients, eventual consistency, and a multi-region failover strategy. For scale, embrace auto-scaling, please. It's so simple, and it's a great benefit. Reduce single points of failure, partition your workloads, have a failure-driven design like embedding requests and doing request-level caching. And of course, do chaos, but again, chaos under load to make sure that what you think is true is actually true. For variance, engineer your operations as much as possible to make those automatic. Understand and socialize the cost of variance and prioritize the support. If you have a centralized organization, and most organizations do, prioritize by impact to make sure that you're as efficient as possible. On change, you want automated delivery and you want to integrate your best practices on a regular basis. And again, solutions first, team second. There's a lot of technologies that support these strategies that Netflix has open sourced. If you're not familiar with it, I think a lot of people are, go check out Netflix OSS. And also check out the Netflix Tech blog, where there are regular announcements about how things are done at Netflix, how things are done at scale, announcements about new open source tools like Visceral, which is the tool that generated the visuals we've been looking at throughout. And I think we're out of time at this point. Do we have time for questions, or should I just take it out?
Outside if you can.
All right,
Thanks,
cool.
Josh.
Well, I pushed the limits. Thank you very much.
Thank you, everybody.